Imagine a future where continents run on invisible currents of pure hydrogen, cities powered by silent fuel cells, aircraft slicing through the sky on electric plasma engines, and electrolyzer farms glowing like neon blue constellations scattered across vast desert plains. In this future, the world's clean energy grid pulses like a living organism, balancing wind, solar, nuclear, and green hydrogen in perfect harmony. But here's the twist. None of this future happens unless we solve one of the hardest engineering puzzles humanity has ever attempted. Scaling hydrogen isn't about marketing slogans or political announcements. It's about building machines that bend physics without breaking, transforming electrons into molecules with surgical precision, and surviving real-world conditions far harsher than any lab has ever simulated. This isn't just clean energy, it's frontier technology. And today, we're stepping straight into the engineering reality behind the world's most futuristic fuel. Hydrogen has been called many things over the past decade. The fuel of the future, the missing link in a net-zero energy system, the molecule that will decarbonize everything electrification can't reach. But somewhere between the glossy renders and the billion-dollar headlines, the world lost sight of something essential. Hydrogen only works if the technology behind it works. Electrolyzers and fuel cells aren't abstract ideas. They are machines, governed by chemistry, physics, thermal dynamics, materials science, and engineering tolerances. And as the world raced into the hype cycle around hydrogen, announcing gigawatt-scale projects long before pilots had even been tested, an uncomfortable truth emerged. Scaling hydrogen is brutally difficult. To understand why, we need to look not at the fantasies surrounding hydrogen, but at the actual machinery that makes it possible. Electrolyzers are often described as simple devices that split water into hydrogen and oxygen using electricity. But that description hides the complexity under the hood. A modern PEM or alkaline electrolyzer is a tightly calibrated chemical system operating under high pressure, high temperature, and constant electrical load. Every component matters: membranes, catalysts, seals, power electronics, thermal management systems, water purification systems, pressure vessels, and balance of plant subsystems. And every one of these components must work together flawlessly for thousands of hours. The problem arises when you attempt to scale this up, not from kilowatts to megawatts, but from megawatts to hundreds of megawatts or even gigawatts. Electrolyzer stacks that perform well in controlled laboratory settings or early pilot deployments often struggle in real-world environments where power fluctuates, temperatures swing, and the systems must continuously balance efficiency with durability. When electrolyzers ramp up and down in response to intermittent renewable energy, the membrane expands and contracts. The catalysts degrade. Water purity requirements tighten. Thermal stresses increase. These forces accumulate over time, shortening stack life and increasing maintenance. In a world where investors expect multi-decadal asset performance, these engineering realities cannot be ignored. One of the biggest misconceptions in the public narrative surrounding hydrogen is the idea that electrolyzers are already ready for mass deployment. In truth, most electrolyzer technologies on the market today were never designed for the specific type of cycling behavior demanded by large-scale renewable energy. When solar power surges in the afternoon, electrolyzers need to absorb that excess generation. When wind slows at night, they need to dial back, but cycling adds wear and tear. Research has shown that fluctuating power inputs accelerate degradation in PEM stacks. The harsh reality is that the more we try to integrate electrolyzers directly with renewables, the more we expose them to stress conditions their original designs did not anticipate. Fuel cells face a different but equally challenging set of engineering realities. A hydrogen fuel cell is a device that turns hydrogen and oxygen into electricity, water, and heat. But achieving stable, efficient, high-power output on demand is difficult, especially when operating environments vary widely. Fuel cells must remain stable across temperature ranges, load conditions, humidity levels, and transient spikes in power demand. They require extremely pure hydrogen, often 99.99999% purity or higher. They must maintain precise humidity inside the membrane. and they must avoid contamination from trace gases that could poison catalysts. The engineering challenge multiplies when fuel cells are deployed in industrial environments. In warehouses, hydrogen-powered forklifts run across multiple shifts without downtime, demanding reliability comparable to diesel engines. In heavy-duty trucking, fuel cells must endure vibration, dust, thermal shocks, and rapid load changes. In data centers, solid oxide fuel cells must deliver continuous, ultra-high quality power, sometimes running 24/7 without interruption for years. Each of these applications pushes fuel cells into operational envelopes, where even small engineering weaknesses become critical risks. Scaling hydrogen, therefore, is not simply a matter of building more electrolyzers and deploying more fuel cells. It's about advancing materials science, accelerating manufacturing improvements, redesigning electrical systems, standardizing control interfaces, and integrating complex subsystems that historically haven't needed to work together. It's also about ensuring durability. A hydrogen system with a stack life of 5 to 7 years may work for a pilot, but industries like steelmaking, refining, ammonia production, and power generation need systems that last 15 to 20 years with predictable maintenance cycles. And that means solving the degradation problem, one of the hardest engineering problems in the entire clean energy sector. The promise of hydrogen lies in its versatility. Hydrogen can store excess renewable energy, power industrial heat, fuel aircraft, support long-duration grid stability, and decarbonize chemical feedstocks. But versatility means nothing if the underlying technology cannot scale. And this is where the conversation often becomes distorted. Hydrogen skeptics argue that electrolyzers are too expensive and fuel cells are too fragile. Hydrogen evangelists insist that cost curves will fall quickly, just like solar panels and batteries. But the truth lies between these extremes. Scaling hydrogen is possible, but not without overcoming fundamental engineering obstacles. Unlike solar panels, hydrogen devices involve complex chemical processes, specialized materials, and safety-critical systems. They don't scale with simple learning curves. They scale with engineering breakthroughs. One reason hydrogen has struggled to scale quickly is the lack of standardized design. Every major electrolyzer manufacturer uses different stacks, catalysts, membranes, and architectures. Integrating these into projects requires bespoke engineering, custom BOP systems, custom power interfaces, custom water treatment, custom cooling, custom compression. This raises cost and slows deployment. To scale hydrogen the way we scaled renewables, the industry must move from bespoke engineering to modular standardized systems, akin to the way solar moved from custom installations to mass-produced plug-and-play panels. Fuel cells face similar issues. Today's systems are highly engineered, highly customized, and expensive. The path to scale involves moving from low-volume precision manufacturing to high-volume assembly lines with robotic automation, component standardization, and vertically integrated supply chains. It also requires investment in catalyst innovation. Platinum group metals remain expensive, and reducing catalyst loading without sacrificing performance is one of the biggest challenges in fuel cell engineering. If hydrogen is to scale, fuel cells must become cheaper, more durable, easier to manufacture, and more tolerant of real-world conditions. The engineering reality becomes even more complex when we consider how hydrogen interacts with the broader energy system. Hydrogen cannot scale unless we address water supply, land footprint, transmission infrastructure, and storage. Electrolyzers need clean, deionized water, not groundwater, not untreated industrial water. In arid regions, this requires desalination systems, which add cost and energy consumption. Hydrogen storage requires compression or liquefaction systems, both energy-intensive. And hydrogen transport, whether by pipeline or truck, demands safety controls, sensors, leak detection systems, and pressure regulation technology far beyond what natural gas systems require. So why, despite all these challenges, does hydrogen remain so compelling? Because hydrogen solves problems that no other technology can. Batteries are extraordinary, but they are not well suited for multi-day or seasonal energy storage. Direct electrification works for cars and homes, but not for steelmaking, aviation, or high-temperature industrial processes. Hydrogen provides a molecular pathway, an energy carrier, a feedstock, and a storage medium that can decarbonize sectors electricity alone cannot touch. The future of hydrogen technology is not a fantasy, it is a frontier. Engineers around the world are working on next-generation membranes that resist degradation, catalysts that eliminate platinum, high-temperature electrolyzers that operate at higher efficiency, and solid-state hydrogen storage systems that stabilize the molecule at lower pressures. Fuel cell developers are pushing for higher power density, faster response times, and better durability. Behind the scenes, the industry is moving toward automation, digitization, machine learning diagnostics, and predictive maintenance, unlocking reliability that today's systems struggle to deliver. Hydrogen's greatest breakthroughs won't come from policy mandates or corporate announcements. They will come from materials science, advanced manufacturing, and relentless engineering iteration. Every electrolyzer that fails early teaches engineers how to build a stronger one. Every fuel cell that degrades under load reveals a new insight. Every pilot project that runs into trouble helps refine the next generation. This is the natural evolution of any frontier technology. Scaling hydrogen will be slow, difficult, and expensive, but it will also be deeply transformative. When electrolyzers achieve longer stack lifetimes, when fuel cells become cost competitive, when hydrogen pipelines undergo modernization, and when industrial clusters adopt standardized systems, hydrogen will move from niche to normal. And that shift won't happen with hype, it will happen with engineering. In the end, hydrogen's future depends not on promises, but on physics. Not on marketing, but on materials. Not on slogans, but on science. Technologies that looked impossible 15 years ago are now powering warehouses, data centers, and industrial facilities. Technologies that look impossible today will be mainstream by 2040. As electrolyzers and fuel cells evolve from fragile prototypes into robust industrial machines, hydrogen will evolve with them into the backbone of a clean, resilient, global energy system. The future belongs to the technology that can survive reality, and hydrogen, built on science and engineered to endure, is just getting started.